Hi students, have a nice day. In this section we are going to discuss about the mechanism of electrophilic substitution reaction, some addition reaction and orientation effects. Okay, let's discuss the mechanism. In the last section we discussed about the some electrophilic substitution reaction. For example, halogenation, alkylation, acetylation, then sulfonation, nitration, etc. Okay, so the electrophilic substitution takes place usually in 3 steps. Substitution of electrophile usually takes place in 3 steps. First step is generation of electrophile. Second step is formation of carbocation. It is an intermediate. And in the case of benzene, the carbocation is formed also known as adenine ion, which is stabilized by resonance, and finally a removal of proton. Okay, so mainly 3 steps. First step is generation of electrophile. Second step is formation of carbocation by the attack of electrophile. Okay, attack of electrophile forms carbocation, and this adenine ion is stabilized by resonance, and finally the removal of proton. Okay, first step, generation of electrophile. First step, generation of electrophile. In the case of halogenation, okay, we discuss halogenation, nitration and alkylation, acylation, etc. In the case of halogenation, the chlorine molecule, the catalyst, you know that anhydrous AlCl3. Anhydrous AlCl3. And AlCl3 is a Lewis acid. Okay, so this chlorine is given to the AlCl3, which forms, okay, this bond is shifted, which forms Cl plus ACl4 minus. Okay, ACl4 minus. So this is the electrophile E plus. Electrophile E plus. And in the case of alkylation, CH3Cl. Here also we use anhydrous AlCl3. AlCl3 that gives, okay, this is moved to the AlCl3, we get CH3 plus AlCl4 minus. Same pattern. Instead of chlorine, methyl group comes. Okay, another one, acetylation. In the case of acetylation, CH3C double bond OCl plus AlCl3. Okay, Friedel-Crafts catalyst, that we get CH3C double bond O plus electrophile. Okay, so the electrophiles are Cl plus CH3 plus CH3C double bond O plus AlCl3. Sorry, AlCl4 minus. Okay, AlCl4 minus. So this plus is for this carbon atom, carbocation, electrophile. And in the case of nitration, we take a concentrated nitric acid and a sulfuric acid. It takes place in 2 steps. The first step is HNO3. So HNO3 can be written as OH double bond O. This is nitric acid. And sulfuric acid, this is the first step. Step 1. Sulfuric acid, we can write that HOSO3H. H2SO4. H2SO4 can be written as HOSO3H. Or you put double bond OH. Okay. Then here the sulfuric acid is act as an acid, and this nitric acid is act as a base. Okay, an acid base. Acid which furnishes, which gives H plus ion, and base which accept the H plus ion. And what we get? We get O, N double bond O, OH, H plus. Okay, so this H plus, this is added to oxygen atom. And also we get HSO4 minus. Okay, oxygen get the electron, so SO3H plus O, HSO4 minus. In the second step, nitric acid, O, N double bond O, OH, H plus. Okay, here is one positive charge. The positive charge is also written here. Okay, here you write. And this electron is shifted to the oxygen. We get NO2 plus. Okay, this species. And the nitrogen loses its electron, that's why becomes nitrogen is positive. 2 oxygen atom, then plus water. So in the nitration, an acid-base equilibrium is exists. Sulfuric acid is act as an acid. Nitric acid is act as a base. Okay, an acid donate H plus ion, and a base accept the H plus ion. So these are the different steps in the formation of or generation of electrophiles. Okay, chlorine electrophile, methyl electrophile or generally alkyl electrophile, acyl electrophile, and nitronium ion. Okay, NO2 plus. Then in the second step, the attack of electrophile, which forms a carbocation intermediate. Okay, so that's about the first step, generation of electrophile. Okay, in the next step we discuss the attack of electrophile, and this electrophile will create or make a carbocation. Okay, so let's discuss the second step, formation of carbocation. Formation of carbocation or adenine ion. In the case of aromatic hydrocarbon, the positive ion is also known as adenine ion. Okay, so here we take the benzene. Okay, benzene. And generally we can take E plus. There are many E plus, Cl plus, NO2 plus, CS3 plus, CS3CO plus, like that. So for generalization we take E plus, electrophile. And this pi electron is donated to the electrophile. Pi electron given into the electrophile. We get an intermediate. You know that each carbon contains hydrogen atom. Okay, 6 carbon contains hydrogen atom. This pi electron is moved to the electrophile. So any one of the carbon atom get attached by the electrophile. The other carbon become positive. Okay, electromagnetic effect you studied. Electromagnetic effect. So electrophile is added to benzene ring. We get adenine ion. Adenine ion. Or a carbocation. So how a adenine ion is formed? By the attack of an electrophile. Okay, when electrophile attack the benzene ring, an adenine ion is formed. So that's why the second step is formation of carbocation or arenium ion. This arenium ion is stabilized by resonance. Okay, let's discuss the resonance. The arenium ion is stabilized by the resonance. Okay. H, E, then H plus. This is the structure. And this pi bond is shifted to this side. Between these two carbon atoms, we get the arenium ion like this. Positive charge comes here. And a double bond comes hydrogen, hydrogen, electrophile. And one more thing you understand that this carbon become sp3 hybridized. Okay, after the attack of electrophile, the electrophile attached carbon atom is sp3 hybridized. It's a very important thing. And the double bond, also one double bond is there. Okay, so positive charge comes on this carbon atom. Another possible resonance is this bond is shifted to this side. We get another resonance structure. Positive charge comes here. H, E. Okay, when the pi bond shifted to this two carbon atom, the positive charge comes on here. That is why we can write the resonance hybrid. The positive charge is resonating the benzene ring. Okay, the positive charge is resonate in the benzene ring. Up to this from this carbon atom, the positive charge comes to this carbon atom. And the aromaticity of this intermediate is lost because the complete conjugation doesn't take place. And moreover, this carbon atom is sp3. Okay, a complete conjugation, the complete resonance is lost because this carbon atom is sp3 hybridized. Are you clear? So this is the second step, formation of carbocation or arenium ion. That arenium ion is stabilized by resonance. Clear? Okay, the last step is removal of proton. Okay, removal of proton. So I erase the resonance structures to show the removal of proton. All these things is given in your textbook. Then the third step is removal of proton. Removal of proton. That structure we consider. Hydrogen or electrophile. Okay, no problem. Just reverse. Electrophile comes in the hydrogen place, hydrogen comes in the electrophilic place, no problem. Then this carbon atom is positive and one more hydrogen is there. Here, this hydrogen is removed. Okay, that hydrogen is removed and this bond is shifted to two carbon atoms. We get electrophile, pi bond. Okay, now it become aromatic. After the removal of this proton, okay, H plus, and this H plus combines with, okay, this H plus combines with AlCl4 minus or HSO4 minus, we get HCl plus AlCl3. This is very important. Okay, when you add AlCl4 minus here, the byproducts HCl and AlCl3. A very simple mechanism. The third step is removal of proton. The proton is attached to the carbon atom. Also the carbon atom possesses or it's contain electrophile. That hydrogen removes as H plus, and the pi bond or the double bond between the two carbon atoms, the positive charge is neutralizes because electron pair comes. Okay, it removes as H plus. So that electron is added to the positive carbon, that is carbocation carbon, and finally we get the substituted benzene. Okay, electrophilic substituted benzene. So that's about the mechanism of electrophilic substitution. Yes, next we discuss the addition reaction. First one is addition of hydrogen, that is hydrogenation. Under a special condition or vigorous condition, that is at a high temperature and pressure, in the presence of a nickel catalyst, benzene undergo hydrogenation and gives cyclohexane. Okay, so in the addition reaction, first one is hydrogenation. Benzene undergo hydrogenation, H2, in presence of nickel catalyst at a high temperature and pressure. Okay, at a very high temperature and pressure, we get cyclohexane. That is one of the reaction. And this is a benzene. The next one is halogenation. In the presence of UV light and excess chlorine, in the presence of UV light and 3 moles of chlorine atom. So we write 3Cl2 in the presence of UV light. That's very important. In the presence of AlCl3, we get hexachlorobenzene. Okay, and here the temperature is 500 Kelvin. Or in the presence of UV light or high temperature, we get benzene hexachloride. Okay, benzene hexachloride, hydrogen, chlorine, hydrogen, chlorine, hydrogen, chlorine, hydrogen, chlorine, hydrogen, chlorine, then hydrogen, chlorine. So this is a benzene hexachloride. And is shortly written as BHC. What is the formula of this compound? The compound formula is C6H6Cl6. And it is known as, the commercial name of this insecticide is gamexine. Okay, 2M is there, gamexine. The commercial name is gamexine. And also it is known as 666. The compound is also known as 666 compound and is a powerful insecticide. Okay, gamexine, that is BHC is a insecticide. Okay, and is also toxic. You remember that. So 3 names: benzene hexachloride. It is known as BHC, gamexine, or 666. Okay, you know that this number is a devil's number. The next is combustion. Combustion of benzene gives carbon dioxide and water. Okay, so the third reaction is combustion. First one is hydrogenation. The second one is chlorination in the presence of UV light. And the third one is combustion. C6H6 benzene. Okay, C6H6 plus 7.5 O2 gives 6 CO2 plus 3 H2. Okay, also you can write that 15/2 oxygen, no problem. 15/2 oxygen. 7.5 O2 is also written as 15/2 oxygen. So these three are the addition reactions. Okay. Then next we discuss the directive influence of functional group in a mono-substituted benzene. Okay. Directive influence of functional group. Directive influence of functional group in a mono-substituted benzene. Also it is known as orientation effect. And two type of orientation: ortho-para directive groups. Ortho-para directive groups, and the other groups meta-directive group. A simple concept. As you know that positive resonance effect and negative resonance effect, plus R effect and minus R effect. So suppose already one functional group is present in the benzene. Okay, already one functional group or a substituent present in the benzene ring. That group is directed the incoming electrophile into either ortho or para position, or it is directed to the meta position. Okay, once again, already the benzene is mono-substituted. That is already a functional group or a substituent present in the benzene ring. The incoming electrophile is directed towards either ortho or para position or meta position. And first is ortho-para directive groups. Okay, the first one is ortho-para directive group. So the directive influence is also known as orientation. Okay, orientation of the functional group. Orientation effect. First of all, we have to discuss the ortho-para orientation. Ortho-para directive groups. Ortho the O is a small. Ortho para directive groups. The positive resonance group. Plus R groups. What are the plus R groups? OH, halogens. Okay, halogens. Fluorine, chlorine, bromine, iodine. Okay. Then alkyl groups. Then alkoxy group. OR group. Then ANH2 group. ANHR group. ENR2 groups. Then ENHCOR group. Okay, or NHCOCH3 groups. These groups are positive resonance effect groups. Okay, these groups are positive resonance groups, and these groups direct the incoming electrophile into ortho-para direction. Okay, so let's discuss how it is ortho-para effective groups. Okay. First of all, we write phenol. This is a phenol. Okay, phenol, the resonance effect, the resonance of the phenol is O plus H, then negative charge, and the 2 pi electrons. This bond is shifted to the carbon atom, and there is a pair of electron, a negative charge. and oxygen become positive. Okay, this oxygen become positive. Functional group nearest 1-2 position is known as ortho position. So now the ortho position is having an electron density, and it has also another resonance structure. The functional group decides the density of electrons. So now the negative charge or the electron is at the para position, 1-4 position. 1, 2, 3, 4. Okay, 1, 2, 3, 4. So 1-4 position, that is para position. Now the electron density is more at a para position. And another resonance structure is, we have another resonance structure, a negative charge, double bond OH. Then this is another resonance structure. And look at the resonance structures where the electron density is accumulated or where the electron density is ortho position, para position, again ortho position. So these groups are ortho-para directive group. The incoming electrophile easily attached. Okay, the incoming electrophile easily attached to either ortho position or para position. Okay, so we get ortho-para products. Are you clear? Yes. So it's a very important. The function group OH, halogens, and remember that halogen is minus inductive group, minus I group. Electron withdraw from the benzene ring. However, it is a positive resonance group. So even though halogen is ring deactivating groups, the resonance effect will decide the ortho-para effect. Okay, actually minus I groups are meta-directive. Okay, minus I groups are meta-directive. However, halogen has positive resonance effect. That's why they are ortho-para directive group. Okay, they are ortho-para directive group. And next is meta-direction. Okay, meta-directive groups. In the case of minus I groups or minus R groups, the incoming electrophile get attached to meta position with respect to the functional group. Okay. The next we will discuss meta-directive group. Meta-directive groups. The groups with the minus R effect or minus I effect. What are the groups which are having minus R effect? NO2, C triple bond N, COOH, CHO, C double bond O, that is keto group, SO3H. Okay, these groups are minus R groups, that is negative resonance effect groups. Also they are minus I groups. These minus I groups, okay, these minus I groups withdraw the electron from the benzene ring and the incoming electrophile goes to meta position. Okay, let's take what happens. Let's take a carboxylic acid, benzene. The one hydrogen is substituted by carboxylic acid group. That is benzoic acid. Benzoic acid. So here the oxygen is more electronegative. That's why the electron is moved from the benzene to the functional group. The group becomes negative and the carbon on the benzene ring, this carbon, become positive. So CO minus OH. Okay, when this bond, this pi bond is shifted to oxygen, the oxygen becomes negative and 2 other pi bonds are there. Okay, also we can start from this, no problem. In any direction you have to draw the resonance structures, no problem. So here this bond shifted. The same pattern you will get. Then what happens in the next step? Resonance structure. Okay, double head arrow. This pi electron shifted to this side and we get the structure. Positive charge comes at the para position CO minus OH. Okay, and it has another resonance structures where this electron comes into these two carbon atoms. Okay, come in between these two carbon atoms, and the structure of that molecule O minus OH. So the positive charge comes at the ortho position again. Then what happens when electrophile comes? Electrophile is positively charged ion or electron deficient. The electrophile, is it attached to this carbon? No, it is positive center. The positive electrophile doesn't attract to the positive centers. And also this carbon, electrophile do not attach to the para position. Then again ortho position. And the possibility of attach the electrophile only at meta position. Meta position is electron rich. Okay. So the group which having minus R effect or minus I effect except halogen. Okay. Halogen is ortho-para influencing group. So the groups which are having minus R effect, the incoming electrophiles get attached to the meta position. Okay, it's very important. The incoming electrophile get attached to the meta position. Then positive resonance group, plus I groups and halogens, they are ortho-para directive group. Okay, let's check what happens. Phenol is nitrated. Okay, in the textbook there is no reaction, but we will understand that what happens. Phenol is nitrated. Phenol is ortho-para influencing group, ortho-para directive group. So it's nitrated. HNO3. Nitration. Is nitrated, we get orthonitrophenol. Orthonitrophenol and paranitrophenol plus OH NO2. That is directive influence. If already one functional group are present in the benzene, this functional group decides the attachment of electrophile, or that functional group direct the electrophile into ortho position and para position. And this para product is a major product. This is a minor product. Remember that. So nitration of phenol we get orthonitrophenol as well as paranitrophenol. Then let's check what happens on electron withdrawing groups. COH in the benzene ring. Nitration with a concentrated HNO3 and a concentrated H2SO4. Here dilute nitric acid is enough. When you take concentrated nitric acid and concentrated sulfuric acid, two ortho position and one para position is nitrated. That is a different product. When you take dilute nitric acid, you get orthonitrophenol and paranitrophenol. When you take concentrated sulfuric acid and concentrated nitric acid, you get another product. Okay, I will write. So here the COH group. This COH group is meta-directive and the incoming electrophile is attached to the meta position. the incoming electrophile NO2 plus is attached to the meta position, not at ortho and para position. Okay, similarly nitro groups are minus R group. When nitrobenzene is again nitrated, it will produce meta-nitro, okay, meta-dinitrobenzene. Then I will give the answer for when you take, or what happens when you take concentrated nitric acid and concentrated sulfuric acid is taken. The product is, okay, here is, we will write, the product is picric acid. That means to ortho position and para position is substituted. When you take dilute nitric acid, you get orthonitrophenol, para-nitrophenol. But when you take concentrated nitric acid and concentrated sulfuric acid, the two ortho position and the para position is substituted. So this compound, the common name of this compound is picric acid, and the IUPAC name is 2,4,6 trinitrophenol. Okay, what is its IUPAC name? 2,4,6. 2,4,6 trinitrophenol. Okay, from the phenol it is obtained. That is known as picric acid. And one more small topic, a carcinogenity of the aromatic compounds. Okay, aromatic compounds are toxic. They are carcinogenic. That means more than two, that is 3 or more benzene rings are fused, they causes cancer. Okay, so high number of benzene ring or higher hydrocarbons, they causes cancer. It mute, it transform the DNA, and the cancer cells growth is very fastly takes place. And remember that one example is 1,2-benzandrazine. Okay, one important product is 1,2-benzandrazine. It is carcinogenic. An example is given. This is anthracene. 3 benzene ring fused. It is called anthracene. And it's a first position. 1 and 2. In 1 and 2 position, there is one more benzene comes. It is called benzandrazine. 1,2-benzandrazine. Okay, you can put alternative double bond, no problem. So the polynuclear compounds, okay, or the hydrocarbon which contains more than 3 benzene ring, they are usually carcinogenic, they are toxic. So please avoid the contact of these chemicals, okay, that will cause cancer, skin cancer. Then if the DNA is transmuted, breast cancer, chest cancer, like that. Okay, so we will finish the chapter hydrocarbon. In the next section we will start a new chapter. Thank you.